Hi, and welcome to part 3 in the video series on creating DLX Architecture Simulator. Today we're going to pick up where we left off last time, and we're going to continue working on our state machine, and continue fleshing that out and getting it much closer to being usable after today's video. Um, so to start with, I'm just going to go over one change that I made since the last video. It's a very minor change. Instead of using the typedef for uint that we used to have, well, I'm now including the standard integer header, which is part of the C standard library. And the reason for that is because we want our integers to be universal. So before, when we had typedef unsigned signed int uint, this could be a 32-bit integer like we want, but it could also be a 64-bit integer depending on what the architecture gives us. So Windows would always give us 32 bits, whereas if you're using GCC on Mac or Linux, it would give you 32 or 64 depending on what type of system you're using. So standard integer lets us just have a consistent value. So that means you have to make some changes in state handler, where we switch from a uint to a uint32t, so that it's always a unsigned 32-bit integer, and also inside of the state for the instruction. And then the other place is the register file handler, where these are all 32-bit registers, so we want uint32t there as well. The other reason we're going to need this is because our cycle counter, to count how many cycles our machines run through, it's going to need to be a 64-bit integer to handle massive numbers, and a 64-bit integer is an insanely massive number. It's like 18 sextillion or so, so it's good enough to count for a long time, hopefully. So we're going to continue on developing now that we've got that out and sorted out. So what we're going to start with is we're going to start by creating another header file, and we're going to call this one instruction handler, and we'll set up our header guards. Instruction handler h, and then we'll define it. And then endif. So this is where we're going to have all of our instructions. So we're going to create, to start, a function handler. So instruction and then void. So this is going to be our function pointer for instructions, and it's going to be a void return type, and then it's going to take in a void pointer. So the reason it's a void pointer is because a void pointer is kind of like, it's like saying, just give me memory, just give me data. I don't even care what it is. I don't care what format it's in. Just toss it in here. So you could pass in an int pointer, you could pass in a char pointer, whatever. And the reason it's really nice is because it's a way for us to pass in 3 integers, let's say, and we could pass it in as a block of data, and then we could just pull out the 3 integers. And it doesn't need to have, oh, we're going to have one instruction for R type, we're going to have one function pointer for I type instructions, we're going to have one function pointer for J type instructions. It lets us have one pointer for all of them, and then each one can take in the data and pull it out however it likes. So it's just a nice way of being able to do that. So that gives us something we can put into our state now. So if we go back to state handler, we have a function, so we can go to and do. So first of all, we can start by including inside the DLX sim, maybe no, let's just include it here as its own thing. Include instruction handler. And now we can go down. Oh, see, that's good. So we should call it something else then. Let's call it instruction function. That's good enough. So we can say instruction function. Oh, whoops. I am forgetting how to do this already. So we need to do that. Actually, let's just shorten this and call it a instruction func. And then we can go instruction func function, or actually function. So this is going to be the function that this state this state will be calling. Because we're going to have, at the beginning, we're going to have one state, and then once we expand to a multi-cycle data path, we're going to have 5 states, so each state will have its own function to execute when it's its turn. So that's good enough for now. Just give us something else to put in there. So let's go to now the state machine.c. There we go. And so last time we created a state variable and we just set the current stage to fetch, the instruction to 0, and everything else in there is, it can't be set yet because they're not just they're not something we can null or set to a default value. So what we'll do now is we'll take our state machine and we will add this. Yes, we got to find our state machine.h here, so we can add the state to the state machine. So right now our state machine has status, error, and registers. So let's add states. So we're going to have multiple states later. We're just going to have one right now. So state, and then state. We'll give it a name state. So we will, inside of state machine.c now, add our state to the state machine. So sm state equals current state. And that's a poorly named variable because we're going to have multiple in a bit, but we will need it. So that's a pointer. So should we have? Do we want state? Let's have states as pointers. Actually, yeah, that's a good idea. Now it's very easy to pass by reference. We don't have to pass by use address in operators and all that kind of stuff. We can just keep it consistent. Makes it easier to set it up. So now let's set up our registers. So registers. Strs. Current registers. And that should be okay because we should only have one set of registers. But we'll malloc some memory for it. Malloc size of registers. Alright. And then we want to initialize registers. Actually, let's do this the same way we did our state machine, where we have a create registers, and it will return a register pointer. So inside of our register file handler.c, we'll say include registers, register file handler, and actually first before that we should include DLX sim, and that's to give us our stdlib, which we can use for mallocing. So we want void create, actually registers star create registers, and that's what we called here. And then inside of our register file handler.h, we will create function declarations, and we'll say registers, create registers. And now state machine will be able to call it, and it'll call this. So here we'll have registers r equals registers star malloc size of registers. And then we'll have enough memory to store all of our registers in one continuous block. And then we'll say initialize registers, and we'll pass in r, and then we'll return registers, or r, sorry. So obviously we'll want to have a int status equals, and just like we did in state machine here, where it's sm general init error, we'll add to our errors.h, and we'll say register errors, and we can use the same values. So reg no error equals 0, and we'll just tab all these over so it's nice and clean, because I like the look of tabbed values. Define reg general init error -1. So now we can say reg general init error, and then status equals, and then if status less than 0. And here we're doing log and then set the error. So we can do to do log this. I guess I should follow the consistency. So add logging, and then here we can't really set error and return it. So what we'll do here is we'll just handle this, and we'll say destroy registers, and then pass in r. And this is because what we want to do is, if we can't initialize the registers, there's no point even having the rest of our system in place. And then at this point r will be equal to null, so we'll return null. And then in here we can say with current registers, we can say if current registers equals null. Then what we want to do is we want to say sm status equals sm register init error, and then else, and then in there we want to put the, actually let's take these brackets, we don't need them, and just add extra lines. But yeah, so we can have if the current register is null, then register init error. Otherwise, sm initialized, and then what we return is sm status. So now we're returning the status instead of just initialized always, and this will handle if it failed to set up the registers. So we want int, or let's declare it up here first. Function declarations int initialize registers. Takes in registers as an argument, and then we'll declare it here. R. And then we'll say, right now there is nothing really to do, so we'll set up default values. So actually I just realized this is something we don't want to do, because we want the very first r0 to be a constant 0. So what we have to do is we have to go registers r equals 0, Actually, let's do R1 or R1. No, let's just do 0. That should set the first one to 0, and then we can pass in R, and it will return. Actually, let's take in this still. But let's just do the mem copy here, and then registers. Actually, let's call this R, and we'll call this one temp. And then we'll say R equals mem so we don't have mem copy there. So we have our temp, and what we're going to do is we're going to say registers R equals the address of our temp, and then we'll just point to it. I don't know how long that's going to last. Well, let's see. We'll see. So let's set up default values. So that will we'll do that later. So we'll set them up to whatever they're going to be. We'll go back to register file handler H, add void destroy registers pointer, and then we'll write the actual function for it. There's R, and we'll say free R. So there we go, perfect. So now that that's out of the way, don't do that. So we have our registers that are created. We have them initialized inside the state machine, and if they're successfully initialized, we don't call an error, we can say initialize. If they return as null, we say it's initialize error, and then inside our destroy our state machine, we will do so clean up the state. So free sm state, and then we'll clean up the registers, sm registers, and then they'll all be good. Actually, we can actually call destroy registers. So this is the nice thing, is we have a function we can call where we can pass in the registers, and then if we want to handle it in a certain way, so if we want to maybe save them all to a file, we can very easily do that instead of just calling free. So maybe we'll implement something like that for state yet. I'm not. Well, do we have something like that for state yet? State handler. Let's create one. Let's do that. So let's go include DLX, include state handler, and then let's go. So let's see, what do we have for state here? State machine .c. It creates one. So let's cut this, and we'll say state current state equals create state, and this way everything can be created inside these functions, and we don't have to add stuff to all these different locations. So state create state, and we'll paste this, and then move this to an initialize state. Where we get a state parameter, and we'll paste it in. S. There we go. And then we'll declare up here the function declaration int initialize state, and then we'll call it initialize um, int status equals, and we'll add more errors here. We'll say state errors, define state, no error, define state general init error. Alright, I move these all over now. The only pain to doing this, but it just looks so clean that I'm okay with that. So I guess I'll move these over one to kind of make it even cleaner. But anyways, that's beside the point. Okay, so state handler now, we can say status equals state no error, and then status equals initialization, initialize state, current state. Actually, let's change this to S now that we have, because we don't really have a current. So initialize state, and then I guess there's no real reason not to return state no error, since there's nothing really that can be done here that's not going to initialize. I guess what we should do is say if S equals null, then we want status to equal S state general init error, or state no memory error. And that's so that we can handle, I guess, so the reason we want to do that is that we can handle, or we can report that there was no memory, so we can say that we know if there's a problem with the memory, or if there's a problem with, the initialization. It kind of gives us more specifications. So let's add that to all of these actually. So define sm no memory error, and we'll say that's -4, and then we'll say define reg no memory error -2, and define state no memory error -2. So let's implement all these now. So state no memory error, else status equals initialize state, and then return status. And then we'll say void destroy state, and state s, and then here we'll just say free s. And then actually let's change this to an int. Let's set all these up like this, and then return state destroy success. So define state destroy success. Let's say 1. Actually, let's change this from no error to success. And that way, we can, let's change all of these to success. And that's just so that we can have a way to say things are going well. So instead of no error, we can say state success. And we should actually change this to state. Actually, yeah, let's do that right now. So state success, and state success. So that way we can just tell us things are going well. So let's set this to reg success, and then we can say if our temp equals null, or our, I guess that can't be null. I don't even know what that would be declared as. So let's say if r equals null, struct unsuccessful declaration, or initialization actually. Let's see if it says there's anything that'll come out. No, there's no real way to tell. So I don't know, maybe it'll equal 0. I don't know. We'll just check if r equals null. Although I don't think it ever will, since it's taking on the address. But it still could, I guess. So if it equals null, we want status to equal no memory error, and then else do the initialize, and then destroy them and return. Boom. And then here we can want this to be an int, and we want it to say return reg success. So now this one here, when we get back the destroy registers, we just don't want it. We don't care about saving it inside status, because if we save it inside status, we're going to return well, actually we could, because we're not actually returning the status here in this one. So, but we'll just leave it for now, and then once we actually return anything other than success, we can check to make sure that the cleanup was successful. So there we want to return status, and inside the state machine, create state. It takes on or returns a state value. Oh, we want to add these to the state handler.h. So at the bottom, function declarations, and we'll have state create state, and then int destroy state, and it'll take in a parameter of a state pointer. Alright, so there we go. Save that. So now state machine has access to that, and instead of going free state, we can say destroy state and pass in sm state. And there we are. We now clean up properly, and we can check for these success or fails. And then we can set that there, and we can go here and go. So actually, we should check for this here. So we create these, and then if the current registers equals null is equal to null, then we want to set the status to register net error. And then otherwise it's initialized, which actually isn't true. So we want to handle these now, I guess. So if so current state's going to return a state, so that should actually return s. Yeah, not status, we want to return s. So we want to check if these are equal to null. So if current state equals null, or current registers equals null, then we want status to be equal to, or sm status to equal, and we can go to the state machine here, or errors, and go to the state machine errors and say, so we can actually delete these, and we can change that to a 2, and we'll call it a general init error. And this is because we don't really care here which one's causing the problem, because we'll be able to check our log once we implement logging, and we'll see, oh, it was a state no memory error that happened. So we can add to do logging, and we'll say the same thing inside register file handler. We'll say to do add logging. Actually, yeah, we should actually implement that the same way. Oh, did I delete it there? I don't want to delete it there. To do add logging. So here we want to go back to state handler and do the same thing, where if status is less than 0, we want to destroy state s, and we want to do add logging. So this way, if there's an error, we'll be able to see in our log which caused the error, and state machine can just handle that. Else, otherwise, we want to that's got to be success. So we want to check if these are successful. Great, we can just log that. Otherwise, the status is going to be SM success. Okay, so now there's a very convoluted and very back and forth way of doing this, but we have initialized our registers, which means nothing more than giving initializing temp was 0, where all of our value, it could be all of the registers initialized to 0 or just the first one. We'll have to find out. And then state will initialize as well, and it has a little bit of error handling. Not the greatest error handling, but definitely better than nothing. So now that that's all done, what we will be able to do now is go back to our main and see that, oh, there we go, gotta change that to SM success does not equal SM error. So all of these, none of them are doing comparison values, though they're all good there. So now in main we have create state machine, which will go to the state machine file and call the create state machine function, which will malloc a state machine, and we should actually handle in here if SM equals null. So first of all, I don't need to add logging at all. SM, let's change a lot of stuff in here actually. Let's change this from ret status to status, and change this to status, and change this to status, and change this to status. So if it equals null, we want status to equal SM no memory error. Otherwise, we want status to equal initialize state machine SM. Initialize state machine is going to return the status, which will either be a general init error or a success. And then, so we can remove that. And actually, I should cut that. And we can remove this. And then we'll check if status is greater than 0, which means success. We can then do this. We can say it's not initialized. It is success on the error part, and the registers are not null anymore because they're initialized here, so we don't annul them. So we have status not initialized, which actually isn't true either because it will be initialized. So let's remove that. Oh no, that was a state machine constant? Yeah, let's remove those because we don't need them anymore, and we're using status differently now. So if status is, we actually don't need the status variable at all. Status equals SM success. Status equals general init error. We don't need the else because it's already going to be equal to success, and then we'll return status. So there's no real reason to kind of take care of that after all. And then we can say here int, and we'll say return SM success, and then inside of our state machine.h we'll change this to an int. So that was just kind of cleaning up some stuff that was unnecessary. There's no real reason to return state machines as a status since we're handling it all a lot cleaner now, and that's not state machine at all. And then we're setting state machines destroy state machine to return as an integer. So now all the destroys will return as ints. All of the, oh, this one isn't actually. So let's change that to an int, and then go to register file handler.c, and it's an int. Okay, so now everything should be returning as integers. all the destroys and stuff, and then we can catch those and see however we want them to be, or see if they are what we want them to be. And then it'll create our state machine, which will in turn create a state and create registers, and then if there's no errors with them, the state machine registers will equal current registers, and the state machine state will equal current state. And then those in turn will create a state, state handler.c. Oh, it's state handle. We should rename that. State handler. So that will create a state, set up the state to be in the instruction fetch stage with no instruction or a 0 instruction, and then the registers will be initialized to the constant one to be 0, so that whenever we try to assign something to it, we'll get errors. Hopefully, we'll see if that's the actual functionality or not. If it is, that's fantastic. If not, we'll have to just add handling to it, where we fake a constant where if anything is assigned to it ever, we just destroy it or handle it somehow. We'll see what happens, I guess. And then initialize registers will set up default values if it needs to, which it doesn't right now, and then destroy registers will free it. So everything gets handled in its own little thing, hopefully properly. So let's build this and see what happens. I haven't built it yet once, so if it works, this is awesome. Oh, triggered a breakpoint. Where is that? Break. So let's see. So registers is null. So let's see if we can figure out where this is happening, since I haven't used the new Visual Studio at all. So we are in destroy registers, and R is null. No, R isn't null. Is it giving me an error because the other two are null? Let's stop and before we get, so where's destroy registers being called? Actually, let's run and see what the stack frame says. So, right. That was because we didn't exit cleanly. Alright. Let's see. It's not gonna, we don't need that. So, call stack. So, create registers. So, status gave us less than 0. So, initializeState machine called create registers. Create registers came in and said status less than 0. So what is status equal to? R0 unable to read memory. Alright, that's fine. But it's not telling us what status is equal to. Is there a way to print status, I wonder? Okay, type anything in here? Status is identified. I don't know what that's for. That'd be kind of neat to look at, though. So locals, no. Watch. So we can't view status at all. So it would be nice to be able to view status. The joys of using a new IDE. Well, let's set a breakpoint. Let's set a breakpoint to 18. And then let's stop this. Let's start it again. So status is negative 8,000. Now, why is it negative 8,000? That's a good question. Well, let's put a breakpoint there, and let's restart. Let's see what we get here. So, reg success is, so if we step to the next instruction, so step over, so it's equal to 0, perfect. So, r temp, and then r is a pointer to r temp, perfect. Is r equal to null? Shouldn't be. So now we go into initialize registers. Oh, and that's why, because it's not returning anything. Perfect. So let's return reg success. That would explain why it stopped working. Okay, so let's run this again. Perfect. So it worked, essentially. It didn't like stop and wait to handle anything, but it did work. So let's go to register or state machine now, and let's put in a scanf. Sure, %d, and that's just going to be to actually that's fine. That's just kind of delay the console window from closing, so we can kind of see if there's any output. Because what we want to do is we want to see and make sure that the constant value is a constant or is 0. So let's see what that initialization did. So state machine registers. Oh, I just realized we're declaring our registers wrong altogether. So what we want to do is so this is actually really nice because this actually changes a lot of things. So in registerhandler.h, we have GP registers, which we do not want to be pointers, and that does not want to be a pointer. So now if we go to register file handler and create, we don't have to do this at all. We can just say this is registers malloc size of registers, because we want the constant to be in the GP registers, not in registers. So here we can go GP registers. Oh, there's my keyboard not functioning. GP equals 0. And then FP registers, FP equals 0. And now what we'll do is we'll set these R FPRs to FP and R GPRS equals GP. So that sets both of these to so that's not working. Let's see what that's there. So R GPRS equals GP. Now I don't know why that's not working. Expression must be a modifiable L value. Don't know why that wouldn't be. Let's try it up here. R GPRS equals GP. Now I wonder if that's because we have the constant in there. Let's try pulling the constant out. See if that fixes things or not. And it does. So that's not good. Because we want that to be constant if we can. Well, what that means is that we're going to have to, in all of our instructions, we're going to have to check if R0 is passed in. And if R0 is passed in, we're just going to have to set that to 0 or pull 0 regardless. So, since that's going to be the way that is, let's actually pull R0 out of the registers, and we'll just handle that as a constant regardless. So I guess a good way to handle that, maybe, let's see. Let's put this into here for now. We'll say define R0 to be 0. So now, if we want to use R0, we would say R0 instead of GP registers R0. So it kind of makes it a little bit annoying, but everything else will be handled with a GP daughter. I guess it will GP star. So what we'll do here is we'll say GPRS equals GP registers. So we do you want it as a pointer? Let's do it as a pointer then, since we don't have to worry about that anymore. So we can say no. We should do it better. So what we're going to do is we're going to say so we'll set these as pointers, and then so yeah, if we want to access R0, we'll have to use R0, not GP registers, and then the pointer symbol, and then R0. We'll have to use just plain R0. So it's going to be a little bit weird to handle, but we'll handle it, I guess. So now let's set up the registers. So we'll have GP registers star GP equals GP registers star malloc size of GP registers strs, and then FP registers FP equals FP registers star. And then we'll say if GP equals null, we will to do add logging. Actually, yeah, let's just do GP equals null or FP equals null, and then we'll set status. We'll set up a status value. Int status equals reg success, and then we'll return status, and that should be a semicolon, not a colon. So if GP is null or FP is null, we want status to be equal to reg no memory status, or no memory error, and then otherwise we can just return, and then else we can set the state machine, or the registers, to be GP and FP. And then inside of our free, we're going to want to free GPRS and free FPRS. And then we can free the registers. So I guess now inside of our state machine.c, we don't have to do any of this anymore, since we won't have a constant in the struct, which there used to be ways to do it in the older C standard, but I guess they removed that. I didn't do too much research on it, but that's kind of what I read up on a little bit. So I guess that's why C++ is kind of nice. You can have just a class and stuff, but we're using C, so there might be ways around it. I'll have to do a bit more research, but we'll see what we can do for now. And for now, we'll just handle it like that. So now our state machine setup is mostly done. So that's where we'll call it now. And the next time, we will start actually implementing the state machine's running function, where we actually start running it and we start cycling through the cycles. And then from there, we're one step away from actually executing states per cycle. And after that, it's going to be wherever that takes us. That's after that, we'll be executing instructions. So we'll be creating functions for instructions, and we'll be decoding instructions and executing instructions, and then that's almost the end of stage 1. So until next video, happy programming.